Hello there, and welcome to the Dull Science. Whether you're tuning in tonight or this afternoon, or perhaps in one of those in-between hours, the ones that sip tea in the hallway while everyone else rushes about, I'm glad you've joined me. If you feel like sharing, I'd love to know where you're listening from and what time it is for you right now. As for me, I'm broadcasting from a little desk in a room that smells faintly of books and lavender, flanked by 3 houseplants, a lukewarm mug of tea, and the faint suspicion I've worn this cardigan inside out all day. So, before you drift off, tap like and subscribe if you're into sleepy science. If not, blink twice and we'll forget this ever happened. Let's begin beneath your feet. You might not have felt anything. No rattling picture frames, no cat bolting under the bed, no gentle wave rocking your glass of water into concentric ripples, and yet the ground beneath you may have moved imperceptibly, but undeniably. This was no ordinary earthquake, not the kind you feel in your bones or hear in the urgent whimper of a dog. This was something stranger, slower. An event that might last days, weeks, even over a month. They're called slow slip events. The Earth, you see, is full of stories it doesn't shout. These stories unfold underground, beneath our cities and forests and oceans, across fault lines so deep and ancient that even the mountains have grown accustomed to their moods. And among these stories are the ones told in whispers, slow slips. To picture one, imagine 2 massive tectonic plates pressed together along a fault line, locked by friction, but always under pressure. Now imagine that pressure releasing, not in a dramatic jolt, but in a creeping slide, like a great wooden door inching open in silence. Over the course of days, one plate glides a few millimeters past the other. A few millimeters, that's all. But when the scale is hundreds of kilometers, a millimeter's monumental. These slips were a mystery for decades. The Earth, it turned out, had been having them behind our backs all along. It wasn't until the late 1990s that geophysicists, watching with new and unusually patient eyes, noticed something odd happening in the Pacific Northwest. Let's head to Vancouver Island, where the ground performs a subtle ballet. There, GPS stations anchored to bedrock began to drift, not permanently, but in cycles. Every 14 months or so, they would shift slightly to the west for several weeks, then ease back to their original positions. The movement was tiny, measured in millimeters, but consistent, predictable, even. It was as if the ground were gently sighing in its sleep. Dr. Herb Draggett and his team were among the first to document this phenomenon. Using a growing network of high-precision GPS stations, they pieced together the first clues that something was sliding silently deep beneath the crust. It wasn't just a matter of random drift or equipment error. The Earth was slipping, but doing so quietly, with all the discretion of a shy librarian. Draggett's work led to the term episodic tremor and slip, or ETS. The tremor part referred to faint, low-frequency seismic vibrations that accompanied these events, sort of like tectonic murmurs, too quiet for humans to feel, but loud enough for sensitive instruments to catch. The slip was the actual movement of the plates. Together, they revealed a whole category of earthquakes we never knew existed. Why didn't we notice them before? The answer lies in the tools. Seismometers, the instruments traditionally used to detect earthquakes, are excellent at capturing short, sharp bursts of energy. They light up when a fault slips in seconds. But if the same energy is spread out over days or weeks, the signal becomes so weak it vanishes into background noise. It's like trying to detect a whisper in a windstorm. You need different ears. That's where GPS comes in. Not the kind on your phone, but survey-grade receivers mounted on metal tripods or concrete piers, recording position data every second of every day. These instruments can detect motion as small as a millimeter, which in tectonic terms is like noticing someone shifting in their chair halfway across a football field. As more GPS networks went live around the world, more slow slip events came to light. They appeared in New Zealand, where scientists with GNS Science tracked movements along the Cascadia Subduction Zone. They surfaced in Japan, where the NIED National Research Institute for Earth Science and Disaster Resilience mapped hundreds of slow slips along the Nankai Trough. Each region had its own tempo, its own periodic rhythm of stress and release. And yet, despite their quietude, slow slips have profound implications. One of the big questions, whether they relieve stress or redistribute it. That is, do they make a future big earthquake less likely, or more? It's a bit like trying to interpret a sigh. Is it the end of tension, or the start of it? Some researchers believe slow slips could be helpful, bleeding off pressure before it reaches a catastrophic threshold. Like loosening the lid on a pressure cooker, just enough to keep it from exploding. Others suspect the opposite, that these events actually transfer stress to shallower parts of the fault, where a major quake is more likely to occur. In this view, a slow slip is not a safety valve, it's a fuse. In Cascadia, this question takes on special weight. The subduction zone off the coasts of Oregon, Washington, and British Columbia is one of the most dangerous seismic regions in the world. It has the capacity to produce a megathrust earthquake, the kind that shakes continents and sends tsunamis racing across oceans. The last one happened in 1700, recorded not in North American documents, but in the tsunami logs of Japan. The next one is coming. We just don't know when. And here's where the slow slips become vital. Every 14 months or so, the deep part of the fault in Cascadia slides quietly, almost meditatively. This may be a good sign or an ominous rehearsal. Researchers like Dr. Heidi Houston and Dr. Ken Krieger have spent years parsing the data, looking for patterns. In 2011, a study from the University of Washington suggested that slow slips may sometimes precede larger earthquakes. The data isn't conclusive, but it's suggestive, like catching a glimpse of a shadow moving through a fog. It's not just the timing that matters, it's the depth. Most slow slips occur deeper than typical earthquakes, 25 to 45 kilometers below the surface. This region, down where rocks are hot enough to deform plastically, may act as a transition zone between locked and freely slipping faults. Understanding how stress moves through this zone is crucial for improving early warning systems. And now we must talk about beauty, because there is a kind of grace in this science, not the grace of simplicity, but of complexity patiently understood. To watch a slow slip through GPS data is to see the Earth not as static and inert, but as breathing. Inhalation, exhalation, the plates press together, then slide, then pause. The cycle continues. We are in a way riding on the shoulders of giants that are always inching toward or away from one another, and we barely notice. There is a moment sometimes when you're hiking in the forest or staring out over a still lake, and you feel the presence of something vast and slow-moving just beyond your senses, something indifferent but not hostile, something alive in its own deep time. Slow slip events are the scientific proof of that feeling. They are Earth's size, inaudible but undeniable. And here's a curious twist. Some of these events are so regular, they've been compared to tectonic metronomes. In Guerrero, Mexico, slow slips occur almost every 4 years, with remarkable punctuality. In the Hikurangi region, certain segments slip every 1 to 2 years, like clockwork. If the Earth has a heartbeat, this may be part of it. There's still much we don't know. Why do some faults slip quietly, while others snap violently? What role do temperature and water play? Why do some slow slips trigger tremor, while others tiptoe past in perfect silence? These are the questions we'll gently unravel tonight, like a geologic sweater knit from layers of time and tension. But already we've learned something. The ground is not as steady as it seems, and stillness sometimes is only an illusion of scale. If you'd been standing on a bluff in British Columbia during one of these slow slip events, you wouldn't have felt anything. Not in your legs, not in your chest. The wind might have ruffled your sleeves. The waves below might have whispered up at the rocks, but the ground beneath your feet would have felt still. And yet, somewhere deep beneath you, the Pacific plate would have been sliding past the North American plate at the speed of a growing fingernail. Not fast enough to make headlines, but just fast enough to catch the attention of something quietly orbiting hundreds of kilometers overhead. Let's talk about satellites. Now I know what you might be thinking. Satellites don't exactly conjure warm fuzzy bedtime images. They're metallic, mathematical, and they beep. But these particular ones, well, they're more like skybound ballet dancers with radar vision. They float in polar orbits, capturing the Earth's surface with a precision so fine, they can detect a bulge or a shift no thicker than a pencil lead. This is the world of INSAR, interferometric synthetic aperture radar. It's a mouthful, I'll admit, but think of it as time-lapse photography for ground movement. Only instead of light, it uses radar. A satellite passes over a region and sends down a pulse of microwave energy. It bounces off the Earth's surface and returns. Days later, the same satellite flies overhead again and does the same thing. By comparing the phase differences between these returning radar waves, scientists can determine whether the ground has moved, even by a few millimeters. And this isn't just theory. INSAR became a household name among geophysicists when it helped detect ground deformation after major quakes in Northridge, California, in 1994, and Kobe, Japan in 1995. But when it comes to slow slip, it's not the drama of broken cities that INSAR reveals. It's the poetry of persistent motion. One of the earliest and most striking uses of INSAR to monitor slow slips came in Japan. In the early 2000s, scientists with the Geospatial Information Authority of Japan began using radar data to detect subtle movements along the Nankai Trough. The findings were remarkable. Ground that had once seemed quiet was actually creeping, not fast enough to set off alarms, but steady enough to matter. To complement these snapshots, we also deploy GPS, specifically dense networks of GPS receivers fixed into the ground, recording positional changes in real time. A single GPS station by itself is like one violinist in a distant room, pleasant but hard to interpret. But hundreds of them, spread across a region and tuned to the same symphony, can reveal the entire movement of a tectonic plate. Take the Plate Boundary Observatory, a network of over 1,100 GPS stations spread across North America, operated by UNAVCO. Since its inception, the PBO has offered an unprecedented look into crustal deformation, including slow slip events in Cascadia and the Basin and Range. Thanks to it, we now have long-term continuous records of slow slip timing, duration and magnitude. One particularly elegant example came from New Zealand in 2010. A GPS station near Gisborne, known as GIS-1, charmingly showed a sudden change in motion that lasted 2 weeks. No tremor, no quake, just a silent sideways nudge. When matched with INSAR data from the Advanced Land Observing Satellite, the event became visible as a surface ripple, like a page turning beneath a magnifying glass. These instruments, GPS and INSAR, are not merely gadgets. They are extensions of our senses. Before them we were deaf to the planet's smallest shifts. Now we hear rustles where once we heard silence. Of course, nothing is ever simple. Even with satellites and sensors, teasing out slow slip signals from noise is a bit like trying to overhear a conversation at a crowded cafe. There's atmospheric interference, vegetation changes, instrument drift, radar waves can be scattered by wet leaves or metal roofs. GPS readings can shift due to snow loading or antenna tilt. To solve this, researchers like Dr. Roland Bergman at UC Berkeley have developed advanced filtering algorithms to isolate tectonic signals. They combine GPS time series, INSAR imagery, and seismic data to create a multi-dimensional model of what the crust is doing. It's like assembling a stop-motion film from scattered frames, but each frame is a whisper from the Earth itself. And what a film it is. You might imagine the Earth's crust as a single monolithic slab, but it's anything but. It's more like a patchwork quilt stitched together from puzzle pieces, each jostling for space, always under pressure. The sensors reveal bulges and sags, microtilts, and warps. Sometimes, the crust behaves like warm wax, sometimes, like brittle porcelain. The slow slip events captured by these instruments are like tiny stress release valves, blinking open and closed with uncanny rhythm. One of the most mysterious patterns ever observed came from the Shikoku region of Japan. There, GPS networks revealed a repeating slow slip every 6 months, as if the Earth were shrugging its shoulders in a ritual dance. When satellites passed overhead, they painted this motion in surreal concentric rings, what geophysicists call interferograms. If you've ever dropped a pebble into a still pond, you've seen something similar. Now imagine those ripples rising from rock. These interferograms are not just beautiful, they're useful. They help modelers refine estimates of fault friction, depth of slip, and future risk. Because while slow slips don't usually cause damage directly, they may influence when and where the next big earthquake hits. And here, a question hangs quietly in the air. Are we watching the Earth relieve its tension or tighten its grip? The answer, it seems, is both. In some areas, slow slip appears to delay major quakes. In others, it may push them closer to the brink. That duality is what makes this science so quietly urgent. We're not just watching the ground move, we're watching it decide. As we peer deeper with better tools, new patterns emerge. In southern Alaska, slow slip was observed in the wake of the 1964 megathrust quake, suggesting that these movements can follow, not just precede, giant seismic events. In the Andes, INSAR has helped reveal slow uplift linked to hidden magmatic systems, blending the line between tectonics and volcanism. Every satellite pass, every blip in a GPS time series, adds a brushstroke to a vast mural of motion. It's as if the Earth has been leaving behind a diary, one entry per week, each written in the language of stress and strain. And though these pages are filled with unfamiliar symbols, we're learning to read them. Because here's the strange comfort, the Earth is never truly still. Its silence is full of motion, and that motion is full of meaning. And thanks to our skybound scribes and hilltop antennas, we're slowly deciphering the story. The next time you walk across a city plaza or a quiet hillside, remember the ground beneath you is likely in motion, not leaping or trembling, but gliding softly with a patience that makes centuries look short. And above you, a silent satellite traces its orbit, catching the slow pulse of continents in flight. Some landscapes wear their violence openly, crumpled mountains, split boulders, coastlines gnawed into strange contortions by forces older than memory. But others, like the Pacific Northwest, hold their secrets just beneath the moss and mist. Here, the trees stretch tall and contented, and the coastlines trace soft curves into the gray-green ocean. But below all that serenity lies the Cascadia Subduction Zone, a fault so long it could cradle a continent, and so quiet that it seems almost polite. That politeness, however, is deceiving. Cascadia is not dormant. It is in fact one of the most closely watched subduction zones on the planet. And the story it's telling, the one we're just beginning to understand, is full of silences that speak volumes. Imagine for a moment, two titanic plates colliding in geological slow motion. The Juan de Fuca plate, a slender sliver of oceanic crust, is being inexorably shoved beneath the North American plate. It doesn't go easily. The boundary between them locks tight for centuries at a time, storing up stress like a bent branch. Then, in one dreadful moment, it lets go. The last time that happened here was on January 26, 1700. We didn't have seismometers then, of course, but we do have oral histories from coastal indigenous nations describing massive shaking and flooding. We have ghost forest stands of trees killed by sudden land subsidence. And we have records from Japan, where a mysterious tsunami arrived with no warning from any local quake. That tsunami traveled nearly 8,000 kilometers across the Pacific. Its arrival was documented in official annals from the Edo period. The Japanese called it an orphan wave. Today, we know its parent, Cascadia. That 1700 quake is estimated to have been a magnitude 8.7 to 9.2. It likely lasted 5 minutes or more, and since then, nothing. No major ruptures, just a long pregnant pause, which brings us to slow slip. Roughly every 14 months, a portion of the fault deep beneath the Olympic Peninsula and southern Vancouver Island begins to shift. It moves slowly, a few millimeters a day, for several weeks, and then it stops. This pattern has been ongoing since we first noticed it in GPS data in the late 1990s. But what does it mean? Well, in the simplest terms, it suggests that the fault is alive, not in a poetic sense, but in a mechanical one. It's doing things, moving, grinding, groaning. That alone is fascinating. But what makes Cascadia's slow slip especially intriguing is where it happens. These slips occur deep down, typically 30 to 40 kilometers below the surface, in the ductile part of the fault. That's a zone where rocks are warm enough to flow slowly, like cold wax, rather than crack violently. Above that, closer to the surface, is the locked zone, the place capable of producing the next megathrust quake. The locked zone isn't moving, not yet. But the ductile zone is, and that raises a question. Are the deep slips loading stress onto the locked zone above? Are they nudging it, ever so gently, toward failure? To try and answer that, scientists have spent decades poring over GPS records, tremor patterns, and complex models of fault mechanics. One study, published in Nature in 2010, by Gavin Hayes and colleagues, used seismic and geodetic data to show that some slow slip events coincide with minor stress increases in the seismogenic zone. In other words, the deep motion could be priming the upper fault for rupture. That's not to say slow slips cause big quakes, but they might set the stage. In fact, one of the most compelling examples of this possibility came from New Zealand. In 2016, a slow slip event was detected offshore along the Hikurangi margin just days before the magnitude 7.8 Kaikoura earthquake. Whether that was coincidence or causation is still debated, but the timing made seismologists sit up a little straighter. In Cascadia, where we're overdue by some reckonings for another megathrust quake, this interplay between silent motion and sudden catastrophe feels especially urgent, which is why we've built a whole suite of instruments to watch it. The Pacific Northwest Seismic Network, in collaboration with the University of Washington and the U.S. Geological Survey, operates hundreds of seismic and GPS stations across the region. These sensors feed data into models that attempt to forecast stress accumulation and fault behavior in real time. We're also using borehole strain meters, devices buried hundreds of meters into the crust to detect the tiniest deformations. And ocean bottom seismometers, launched from research vessels, extend our reach beneath the seafloor. All of this effort is aimed at one central goal: understanding how stress moves through the Cascadia Subduction Zone. Does it build linearly like winding a spring? Or does it surge and retreat, like tides? Do slow slips help or hinder? We don't yet know, but we're learning. For instance, the duration of slow slip events in Cascadia has been remarkably consistent, lasting around 10 to 15 days. That regularity has made them useful natural experiments. Each one adds another data point to a growing archive of tectonic behavior. And there are curious anomalies. In 2003, for example, the slow slip cycle in southern Vancouver Island skipped a beat. No event occurred during its expected window. Some speculated that the fault was behaving differently, perhaps slipping too slowly to detect or temporarily locking up. Whatever the cause, the missed beat served as a reminder. Even patterns that seem clockwork can have surprises. The metaphor I keep returning to is that of a violin string being tuned. Turn the peg too tight, and the string might snap. Turn it gently, and it will stretch. Cascadia is being tuned, slowly, by forces we can only partially see. Slow slip events are one of the few visible turns of the peg. And yet the Earth gives us just enough to be tantalized, never enough to be certain. Some researchers, like Dr. Megan Miller and Dr. Brendan Crowell, have explored the use of machine learning to detect subtle signals within GPS noise, hoping to identify micro-slips or pre-slip phases that traditional analysis might miss. Others are deploying fiber optic cables across the ocean floor to detect seismic waves and strain using distributed acoustic sensing. These tools promise a finer-grained view of what the fault is doing, when it does what it does, and how we might know sooner. Because in the end, that's what this is about. Awareness. Not prediction, not yet, but presence. A way of seeing the land not just as something underfoot, but as something alive with stories, slow and murmuring. So the next time you're hiking in the Olympics or standing on a ferry in Puget Sound, know this. Beneath the ferns and ferry boats, the ground is quietly rehearsing. And we, with our satellites and sensors, are learning the choreography, 1 millimeter at a time. If slow slip events are the whispered conversations of tectonic plates, and stress cycles are the rhythms that shape those conversations, the long, deep breaths of the Earth alternately drawing in tension and exhaling relief, you and I have something in common with tectonic plates. We operate on cycles, days and nights, inhale and exhale, work and rest. Faults have their cycles too, though measured not in hours but in centuries. And unlike us, they don't always complete the cycle cleanly. Sometimes a quake shatters the rhythm. Other times, slow slip takes the stage instead, conducting a quiet and unresolved chord change in the grand music of geology. Let's start with how stress accumulates along a subduction zone like Cascadia. The descending oceanic plate doesn't glide smoothly beneath the continent. It sticks. Friction locks the interface tight. Meanwhile, the two plates keep pressing into one another, bending and deforming the crust. This strain builds silently for decades, even centuries, storing potential energy like a bowstring pulled taut. Then one of two things happens. Option 1, a mega-thrust earthquake. The fault unlocks suddenly, releasing centuries of stress in seconds. Buildings sway, tsunamis rise, and the ground reshapes itself in one great lurch. This is the catastrophic conclusion we spend lifetimes preparing for, trying to understand. Option 2, slow slip. The fault slips, but over weeks instead of seconds. The energy is released gradually, dissipated, without the shuddering shock waves of a traditional quake. It's quieter, less destructive, but it's not necessarily benign. To make sense of how slow slip fits into the earthquake cycle, we need to think not just in terms of magnitude, but of friction and timing. Dr. Yoshihiro Ito and colleagues in Japan have studied this dynamic extensively along the Nankai Trife. They've shown that slow slip events can occur on parts of the fault that are transitional, neither fully locked nor freely slipping. These regions are known as conditionally stable zones. Under the right stress, they can slip slowly. Under different conditions, they might rupture violently. This makes slow slip both a stress reliever and a stress redistributor. It's as if one part of the fault releases pressure, but in doing so shifts that pressure to neighboring regions, perhaps to places that are less forgiving. In 2018, a study by William Frank and Roland Bergman, published in Nature Geoscience, explored this dynamic using models of stress transfer. Their findings suggested that slow slip events can increase Coulomb stress, essentially the slipperiness, on adjacent locked patches of fault. In simpler terms, a slow slip might be the polite knock that wakes a sleeping giant, but the reverse is also possible. A slow slip could gently ease pressure, delaying rupture. The real answer depends on timing, location, and fault geometry. Let's consider an analogy. Imagine a crowd of people pressing through a narrow hallway. If someone near the middle starts to move slowly, they may ease the pressure behind them, or they may jostle others into motion. It depends on how tightly packed everyone is, how ready they are to move, and whether the exit ahead is blocked or open. A tectonic fault is, surprisingly, not all that different. Nowhere is this balancing act more apparent than in Mexico. The Guerrero Gap, a segment of the subduction zone off the coast of southern Mexico, has been the focus of slow slip studies for over 2 decades. Here, GPS networks have documented remarkably regular events every 4 years or so, lasting several months. These events are massive in terms of energy released, equivalent to magnitude 7 quakes, but so slow that they go unfelt. In 2006, a slow slip in Guerrero was accompanied by deep tremor and a change in the stress field that rippled hundreds of kilometers along the fault. Some researchers worried it could trigger a larger quake closer to Acapulco. It didn't, but the risk remains. The takeaway is this: slow slip events are not isolated. They're part of a dynamic system. A fault doesn't just slip and forget, it remembers. Stress accumulates, dissipates, redistributes. The fault evolves with each event, reshaping the landscape of risk. Seismologists use the term earthquake cycle to describe this ongoing process: stress accumulation, fault locking, rupture, and healing. Slow slip events don't break the cycle, they complicate it. And that complexity is precisely why our understanding has shifted in recent years. Back in the early 20th century, seismology was largely event-focused. Earthquakes were seen as singular occurrences, sudden, unpredictable releases of stress. But today, thanks to continuous GPS and seismic monitoring, we've begun to view faults as living systems. Systems that twitch, sigh, stutter. Systems that whisper long before they scream. Dr. Lucy Wallace at the USGS has been working on probabilistic seismic hazard models that incorporate slow slip behavior. By feeding slip rates and tremor patterns into simulations, researchers can better estimate the likelihood of a major quake occurring within a given time window. The models are still young, but they're growing more nuanced with each slip cycle recorded. One of the goals is to understand stress shadows, regions that become temporarily less likely to rupture due to a nearby event, and stress concentrations, where the danger increases. Slow slip events affect both, but the direction and magnitude of that effect depend on the shape of the fault and the distribution of fluids, heat, and friction. And here, we arrive at a delightful twist in the narrative. Water. Fluids within the fault zone can dramatically influence whether it slips slowly or ruptures suddenly. We'll wade into that mystery later on, but for now, know this: the fault stress cycle isn't just a mechanical thing. It's also hydraulic. Like blood pressure in a network of veins, the pressure of pore fluids in fault rocks can tip the balance between stability and chaos. In some places, high-pressure fluids may act as a lubricant, encouraging slow slip. In others, they may weaken the fault enough to promote a sudden quake. Understanding this balance is crucial, not just for academic curiosity, but for public safety. Because here's the quiet truth: we may never predict earthquakes with precision, but we can anticipate behaviors, and slow slip events are among the most consistent behaviors we've ever observed in subduction zones. That consistency gives us a rhythm to follow, like a geologic heartbeat. Each slow slip, each tremor, each GPS twitch adds another beat to the melody. The melody of the fault, it's irregular, yes. It has pauses and crescendos, but it is a song nonetheless. A song of tension and release, of waiting and moving. And if we can learn to hum along, to tap our models and warnings in time with that rhythm, we may yet become better stewards of this restless ground. Because in the end, understanding isn't just about knowing, it's about listening, and the earth in its own way is trying to speak. Tsunamis have a flair for the dramatic. They barrel in like uninvited guests, unpredictable, unstoppable, and rarely subtle. When we think of the forces that summon them, our minds drift to the iconic, a monstrous earthquake, snapping the seafloor upward, displacing water with all the grace of a thrown brick. But what if I told you that the sea can stir without the quake? That a tsunami could rise, not from violence, but from a slow, silent shift beneath the waves? It sounds like the beginning of a tall tale, the kind told by coastal fishermen with weathered eyes. But science, as always, finds truth stranger than fiction. In certain tectonic theaters, it appears that slow slip events, not just the shattering ones, may play a role in tsunami generation. Let's return for a moment to Cascadia, where the deep slow slips happen regularly and the shallow fault zone remains eerily locked. Conventional tsunami modeling focuses on the latter, sudden shallow earthquakes that abruptly shove the seafloor, sending water flying. But over the past 2 decades, scientists have begun to ask a quieter question. What if a slow slip event, if shallow enough and large enough, could deform the seafloor without the dramatic rupture we associate with tsunamis? This idea gained traction in part due to a puzzling event in 2010. That year, off the coast of Indonesia, a magnitude 7.8 earthquake produced a surprisingly large tsunami, one disproportionate to the shaking experienced on land. When researchers examined the seismic signature, they noticed something odd. The rupture had unfolded unusually slowly. It lacked the high-frequency energy of a typical quake, and yet, the vertical displacement of the ocean floor was enough to summon waves over 3 meters high. The culprit, a tsunami earthquake, a term coined to describe events with slow rupture speeds that produce disproportionately large tsunamis. Though not strictly slow slip events in the GPS-defined sense, these quakes occupy a gray area between classic rupture and prolonged slip, and their existence forces us to expand our models. In 2020, a study by Laura M. Wallace and colleagues at GNS Science in New Zealand explored the potential tsunami hazard of shallow slow slip events along the Hikurangi margin. Using ocean bottom pressure sensors and seabed geodetic instruments, the team detected subtle seafloor uplift during a multi-month slow slip event offshore. Though no tsunami followed, the deformation was real, measurable in centimeters. Wallace's work raised a tantalizing question. Under the right conditions, could a slow slip at shallow depth produce enough vertical motion to generate a tsunami? The answer, cautiously, appears to be yes. Here's how it might work. When a fault slips slowly near the trench, the very front edge where the subducting plate dives beneath the overriding one, it can lift or lower the seafloor. The amount of movement might be modest, but if it occurs over a wide area, it can displace a significant volume of water. And because slow slips lack the seismic punch of fast ruptures, their tsunami-genic potential could go unnoticed until waves are already en route. Traditional tsunami early warning systems rely heavily on seismometers. They're trained to detect strong shaking and then estimate whether the magnitude and location of a quake are sufficient to pose a tsunami risk. But if an event unfolds too slowly to generate strong seismic waves, or if the slip is largely aseismic, with little shaking at all, those systems might miss it entirely. This has led to a quiet revolution in tsunami science. Enter the world of seafloor geodesy, an emerging field that uses acoustic ranging, GPS acoustic techniques, and pressure sensors to measure real-time changes in the ocean bottom. By comparing the position of fixed transponders on the seabed to a GPS-equipped surface buoy, scientists can detect subtle shifts in the seafloor over time. And when combined with ocean bottom pressure recorders, they can also detect changes in water column height, often the first clue that something tectonic has stirred. One of the most advanced deployments of this technology is the Seafloor Geodetic Array in Japan. Maintained by the Japan Coast Guard and the University of Tokyo, it spans much of the Nankai Trough. During a 2018 slow slip event, this array recorded centimeter-scale uplift of the seafloor, enough to revise tsunami hazard models in the region. Likewise, the Ocean Observatory's initiative off the coast of Oregon and Washington has installed pressure sensors and seismic nodes on the ocean floor, capturing deformation data in real time. These instruments, while still relatively sparse, offer a tantalizing glimpse into a future where tsunamis could be detected not by the earthquakes that trigger them, but by the ground motion that precedes them. But we're not there yet. In 2011, the devastating Tohoku earthquake in Japan revealed the limitations of traditional models. That quake ruptured all the way to the trench, producing enormous seafloor uplift and a tsunami over 30 meters high. While it was not a slow slip event, it underscored the importance of near-trench deformation, and it prompted renewed focus on improving offshore monitoring, particularly in zones with a history of slow slip behavior. To be clear, most slow slip events don't produce tsunamis. Their slip rates are low, their fault motions typically horizontal, and their depths too great to perturb the ocean's surface. But a subset, those occurring near the trench, at shallow depths, remain a wild card. In the words of Dr. Emile Okal, a tsunami expert at Northwestern University, it's not the size of the earthquake that matters most for tsunamis, it's the speed and direction of the slip, and whether it lifts the seafloor. Slow slip, by its nature, struggles with speed, but it wins on scope and subtlety. The modeling challenge now is to integrate slow slip mechanics into tsunami forecasting. Researchers are building hybrid models that account for both fast and slow fault slip, as well as viscoelastic relaxation, a fancy way of saying that the Earth's crust behaves like both a solid and a very patient jelly. Dr. Diego Melgar at the University of Oregon is one of the leaders in this space. His group is using machine learning to predict tsunami heights based not just on seismic inputs, but on GPS-inferred fault slip, seafloor strain, and ocean sensor data. These models are already being tested in simulation environments. In time, they may inform real alerts. Why does this matter? Because communities on coastlines, from Pacific Islands to North American harbors, don't have time for uncertainty. For many, the warning window for tsunamis is measured in minutes. Every second counts. If a slow slip event can contribute to seafloor deformation that models overlook, it becomes a blind spot, and blind spots are where danger hides. So, we return again to the ocean floor, listening for whispers in the pressure sensors, nudges in the GPS arrays, faint echoes in the radar scatter. Science, in its quiet persistence, is learning to hear those whispers. And in that listening, we may one day know not just that a wave is coming, but that it has already begun, far out at sea, long before the water lifts a single grain of sand. If slow slip events are the breathy sighs of tectonic plates, then tremor is their muttering. The low, grainy murmur of the earth talking to itself deep underground. It's not loud, it's not sharp, it doesn't jolt or wake the furniture, or roll dramatically through the soil. But it's there, rumbling like a kettle left to boil with the lid still on. This kind of seismic activity is called non-volcanic tremor, or more precisely, deep tectonic tremor. It's one of the quieter characters in our seismic cast, but no less complex for it. If anything, it's the one that most resembles the thoughts of the Earth, a kind of low-frequency internal monologue that plays out deep beneath the crust, below even where the slow slip events tend to occur. Let's begin not with a definition, but with a moment. In the early 2000s, researchers studying seismic data from the Pacific Northwest began noticing something odd. Buried within the background hum of the Earth's usual noise, wind, waves, machinery, were long-duration, low-frequency signals that didn't look like typical earthquakes. They weren't sharp enough. They didn't have the clean beginning or abrupt end that seismic events usually do. Instead, they looked like fuzzy blobs in the data, tremors lasting tens of seconds to several minutes, sometimes even longer, and arriving in small clusters. These weren't aftershocks. They weren't noise. They were a new species of seismic life. Scientists like Amanda Thomas, Ken Krieger, and Heidi Houston at the University of Washington dug into the data, tracing these tremors to depths of 25 to 45 kilometers, about where slow slip occurs. And they found something remarkable. In Cascadia, tremor and slow slip are not just neighbors, they often happen together. This co-occurrence led to the term episodic tremor and slip, ETS, which you may recall from our first chapter together. It's a poetic acronym, almost like a jazz duo, one smooth sliding, the other gently rattling. They don't always perform in unison, but when they do, it's compelling. Here's what makes tremor so special. It doesn't rupture the fault, it doesn't cause damage, but it does trace motion. Like the tracks left by a glacier on rock, tremor lets us see where and how slow slip is unfolding, and it offers crucial insight into the nature of the fault at those deep levels. The seismic waves from tremor are dominated by low frequencies, usually below 10 Hz, and lack the impulsive P and S wave arrivals that typify ordinary quakes.
This makes tremor hard to detect using conventional earthquake monitoring techniques. It hides in the folds of background noise, especially during the daytime when human activity fills the data with all kinds of vibrational clutter. So how do we find it? Through clever analysis and persistence. Researchers use cross-correlation and stacking techniques, aligning tremor signals from multiple stations to amplify the common elements and suppress noise. It's a bit like trying to hear a whisper in a crowded room by lining up a dozen microphones and filtering out everything but the shared frequencies. In 2005, Steve Idy and colleagues introduced the idea of low-frequency earthquakes, tiny quakes that occur repeatedly in the same location and generate low-frequency signals very similar to tremor. LFEs are now thought to be the building blocks of tremor, the pops that collectively form the murmuring tremor signal we observe during slow slip. Each LFE is small, magnitude 1 or 2, but together they paint a map of the fault's deep behavior. In Japan, researchers at the NID have catalogued thousands of LFEs beneath the Cascadia Subduction Zone. These patterns show remarkable regularity, and their timing often lines up with slow slip events observed on nearby faults. Similarly, in Cascadia, clusters of LFEs light up like clockwork during the 14-month slow slip cycle. And here's where it gets stranger. Some tremor appears to migrate, moving up or down the fault like a slow-motion landslide of seismicity. In Cascadia, tremor often starts in the southern Puget Sound and propagates northward at rates of 5 to 15 kilometers per day. This migration matches the advance of slow slip, suggesting the two are part of the same physical process. In some cases, tremor bursts behave like aftershocks, triggered by distant earthquakes, or by stress changes within the fault. In others, they seem spontaneous, erupting like waves of thought from within the earth. But what drives them? One leading suspect: fluids. At the depths where tremor and slow slip occur, rocks are hot and pressure is high. Water and other fluids, released from the subducting slab as it heats and dehydrates, can migrate into the overlying mantle wedge and fault zones. These fluids change the mechanical properties of rock, reducing effective normal stress and making it easier for faults to slip, even if only a little. Picture water under pressure, seeping into a door hinge. It doesn't burst the door open, but it might let it creak a little. Tremor is that creaking. There's supporting evidence. Seismic imaging studies have revealed zones of high fluid pressure beneath subduction zones, particularly where tremor and LFEs are most active. And laboratory experiments on rock samples under high pressure and temperature have shown that even small amounts of fluid can dramatically alter fault strength and behavior. In 2017, scientists used a borehole observatory in the Nankai Trough, the Nantro's Eyes project, to directly monitor fault zone conditions at depth. The data revealed changes in pressure and temperature correlated with slow slip and tremor activity. Though still in early stages, this work could one day let us watch the plumbing of a fault in action. Tremor also seems to respond to outside influences. Large distant earthquakes, like the 2004 Sumatra Andaman event, have triggered bursts of tremor in Cascadia, Japan, and New Zealand. This phenomenon, known as dynamic triggering, occurs when passing seismic waves momentarily increase stress along a fault, nudging it into motion. It's as though the fault was already close to slipping and just needed a gentle tap. The fact that tremor can be triggered this way suggests that parts of the fault are perpetually on edge, like a book leaning too far off a shelf. These near-critical conditions are exactly where we expect slow slip to occur, which brings us back to the tremor's role. We still don't fully understand if tremor causes slip or if it's just a byproduct of slipping rock. Some models suggest that LFEs represent tiny ruptures that, when numerous enough, lead to slow slip. Others propose that slow slip creates stress gradients that then trigger tremor. It's likely both, like rain and thunder. One doesn't always cause the other, but they often arrive together. And yet, for all its mystery, tremor has become one of our best tools for mapping fault behavior in real time. It tells us when and where the deep earth is moving, even if the surface stays still. It's also, curiously, one of the most poetic expressions of tectonics, a sound too low to hear, a signal too subtle to shake a building, but too persistent to ignore. If earthquakes are the voice of the earth shouting, then tremor is the whisper it mutters in sleep, or thought, or memory. And with each cycle of slow slip and tremor, we hear a little more of what the planet has been thinking all along.
Of all the suspects in Earth's tectonic mysteries, none is slipperier or more misunderstood than water. Not the rain that falls or the rivers that rush, but the water that hides trapped miles beneath our feet, locked in rock, caught between grains, and pressurized until it behaves more like a conspirator than a companion. Here, in the hidden hydraulics of the earth, we find one of the most compelling actors in the drama of slow slip and tremor. Welcome to the world of fault fluids, a world that might explain how rocks can murmur, why tectonic plates might glide in silence, and what tips the balance between slipping softly and breaking apart. To understand the role of fluids, we must venture into the subduction factory, as geologists sometimes call it. When an oceanic plate dives beneath a continental one, it drags along seawater-soaked sediments and waterlogged minerals like serpentinite and clay. As the plate sinks, temperatures rise and pressures climb. The minerals break down, releasing water molecules that have been chemically bound within their crystalline structure. This process is known as dehydration metamorphism, and it's every bit as dramatic as it sounds, except it takes place over tens of kilometers and thousands of years. The released fluids don't just vanish, they migrate upward into the overlying mantle and crust. They follow fractures, seep through pores, and infiltrate fault zones. And there, under enormous pressure, they begin to meddle. Fluid pressure acts as an invisible hand within a fault. It reduces the effective normal stress, the clamping force that holds two sides of a fault together. Lower that stress, and it becomes easier for the fault to slip. This is a cornerstone of rock mechanics, and it's captured in a deceptively simple equation by Byerlee's law, which governs fault strength. If you reduce the effective stress, you reduce frictional resistance. In 2009, a landmark paper by Emily Brodsky and colleagues in Nature showed how transient fluid pressure changes, perhaps from distant seismic waves or pore pressure oscillations, could trigger tremor in otherwise quiet fault zones. The evidence was compelling. Tremor often occurred where high-pressure fluids were suspected to accumulate, particularly along the plate interface at depths between 30 and 40 kilometers. But these aren't puddles. We're talking about fluids trapped at lithostatic pressures, tens of kilometers below the surface, where water doesn't boil or freeze as we know it. Instead, it becomes supercritical, neither liquid nor gas, but something in between. A state with the density of a liquid and the compressibility of a gas. Think of it as water unbound, nimble, aggressive, and surprisingly good at sneaking into cracks. Geophysical studies support this. Seismic tomography, which maps variations in wave speeds through the Earth, often shows low-velocity zones at the depths where slow slip and tremor occur. These zones absorb seismic energy more than expected, consistent with the presence of fluid-saturated rock. Similarly, magnetotelecic surveys, using natural variations in the Earth's magnetic field to probe electrical conductivity, have revealed highly conductive zones near tremor hotspots. Water, especially when rich in dissolved ions, conducts electricity far better than dry rock. One of the best documented cases comes from the Hikurangi Subduction Zone off the east coast of New Zealand. There, a collaborative team from GNS Science and international partners drilled into the subduction interface as part of the International Ocean Discovery Program. What they found were overpressured sediments, gooey, fluid-rich layers sitting atop the downgoing plate. These fluids, they believed, were intimately tied to the regular slow slip events observed offshore. And then there's the remarkable work from the Nankai Trough in Japan. Through the Nantroses project, researchers drilled deep into the plate boundary fault and installed a borehole observatory, the first of its kind in such an active setting. Among the things they measured, temperature, pressure, and chemical composition. The observatory confirmed what many had suspected for years. The fault was overpressured. Fluid pressures were close to, or even at, lithostatic levels, enough to essentially float one tectonic plate off another. It's this buoyancy, geologists believe, that helps initiate and sustain slow slip. Instead of resisting motion, the fault becomes lubricated. Not in the oily sense, but in the sense that resistance is lowered enough for sliding to occur without rupture. Some researchers refer to this as frictional healing versus dynamic weakening. A dry fault might heal between slips, regaining strength until it breaks violently, but a fluid-rich fault may never heal fully. It slips gently, like a cello string drawn slowly by a bow, rather than plucked by a finger. And fluids don't just affect slip, they also control seismic permeability, how easily waves travel, and how energy is dissipated. A fluid-saturated fault might release tremor, but not earthquakes.
Or, depending on the local stress and chemistry, it might do both. The chemistry, by the way, is wild. In many of these fault zone fluids, researchers have detected unusual concentrations of silica, methane, and even helium-3, an isotope usually associated with deep Earth sources. This suggests that some of the fluids involved in slow slip may be cycling from far below, perhaps even from the mantle wedge. Others are more local, released from sediments and rocks, undergoing diagenesis or metamorphism. In 2015, a study in geology by Kotaro Ujiie and colleagues showed that serpentinite, a hydrated mineral common in subduction zones, can become a key player. When serpentinite dehydrates, it not only releases water, but also weakens dramatically. The combination is explosive: fluid release, strength loss, and stress concentration all at once. Yet even here, nature is ambiguous. Fluids are both facilitator and inhibitor. They can trigger slow slip by lowering friction or prevent larger quakes by bleeding off stress gradually. They can also create fluid overpressure zones, where slip is delayed until a critical threshold is reached, at which point rupture could be more violent than if fluids weren't present. The fault becomes a pressure cooker, and we, above ground, are left watching the steam gauge. This is why fluid modeling has become such a hot topic, no pun intended, in tectonic science. Researchers like André Niemeyer and Christopher Marone have run hundreds of lab experiments on rock samples saturated with fluids, subjecting them to slow shearing under high pressure and temperature. Their findings, the rate of fluid migration, the grain size of the rock, and the temperature all influence whether slip will be seismic or aseismic. In practice, this means we can't understand slow slip, or tremor, or deep fault behavior, without understanding the local fluid regime. It's not just about rocks, it's about the water between them. To map these regimes, scientists now combine geophysical imaging with geochemical sampling, machine learning, and direct borehole observation. A full picture is emerging, blurry but growing sharper, like watching a face resolve in the steam on a bathroom mirror. And what that face tells us is this: the Earth is wet in more places than we realized, quietly soaked, softly pressured, always on the edge of letting go. The next time you see steam rising from a street after rain, or mist curling off a hot spring, think of the fluids far below, slipping through grain boundaries, pressing into faults, whispering to the crust. Because down there, in the dark, water is not just a passenger, it's the driver. The Earth rarely warns us in plain language. It's not in the habit of putting up signs or sounding alarms, at least, not ones we've been trained to hear. More often, it mumbles, it shuffles and twitches. It drops hints in patterns, buried in data, camouflaged in noise, and the challenge for scientists has always been to figure out which of these murmurings mean something, and which are just the planet turning over in its sleep. In the case of slow slip and tremor, those hints are now being translated, syllable by tectonic syllable, into a kind of warning. Not a precise prediction, science still keeps its humility on that front, but a signal soft and steady, that something within the crust is shifting. And with that, we're learning to build early warning systems that don't just react to the sudden jolt of a quake, but that listen for the longer whisper of what's coming. Let's start with the traditional model of early earthquake warning. A network of seismic sensors, spaced out across a region, each listening for fast-moving P waves, the first waves to arrive when a fault ruptures. These waves move faster than the damaging S waves that follow, and so in principle, you can detect a quake as it starts, and use the time between P and S wave arrivals to issue a warning. This works. It's the foundation of Japan's early warning system, of Shake Alert on the US West Coast, and of similar systems around the world. But it only works once the earthquake has already begun. Slow slip events don't begin that way. They unfold beneath the threshold of P-wave detection. They don't trip seismic alarms or rattle dishes. Instead, they register on GPS instruments, infrasound monitors, strain meters, and sometimes, not always, as low-frequency tremor. Their onset is subtle, but they may herald something larger. This is why, over the past decade, scientists have started to explore how we might incorporate slow slip into early warning systems. Not as an immediate trigger, but as a background condition, an atmospheric pressure reading for the Earth's crust. The goal is to understand whether slow slip can increase the likelihood of a damaging quake in a nearby locked segment of fault, and if so, to detect those slips in near real time. That's harder than it sounds. GPS data is precise but noisy. One station moving a few millimeters per day might be enough to suggest a slow slip, but it might also be thermal expansion of the ground, snow loading on a rooftop, or even a curious elk nudging the antenna. To separate signal from noise, you need lots of stations, good modeling, and clever algorithms. Enter the next generation of real-time geodesy. Institutions like UNAVCO and the EarthScope Consortium have deployed dense networks of GPS stations equipped with real-time telemetry. That means data is transmitted immediately, not just stored and retrieved later. Combined with seismic and infrasound data, these streams can feed into software that identifies deformation patterns as they emerge. In 2020, a study by Diego Melgar and Gavin Hayes demonstrated how real-time GPS, combined with machine learning, could detect the onset of fault slip during the 2019 Ridgecrest earthquake sequence in California. Though Ridgecrest wasn't a slow slip, the methods they used are now being adapted to slow slip zones. The idea is to catch a slip, not just after it finishes, but as it begins, and to issue a change in alert level, even if a quake hasn't happened yet. Think of it like watching a volcano inflate. You don't know if it will erupt, but the motion is meaningful, you want to know about it. Some systems are already experimenting with this kind of logic. The Japanese GeoNet system uses real-time kinematic GPS to monitor deformation, and researchers at Kyoto University are exploring how shifts in strain rate might precede larger quakes along the Nankai Trough. In New Zealand, GNS Science has developed protocols to assess tsunami hazard in response to observed offshore slow slips, particularly where those slips coincide with shallow trench segments. But these tools are only as good as their resolution, which is why scientists are also turning to fiber optics. A new technique called distributed acoustic sensing turns existing fiber optic cables, such as those used for internet traffic, into dense arrays of seismic sensors. By sending pulses of light through the fiber and measuring how that light scatters when the cable is stretched or compressed, DAS can detect motion at intervals of just a few meters, over tens or hundreds of kilometers. Suddenly, the Earth's crust becomes a readable scroll, densely sampled and richly detailed. In California, DAS has already been used to monitor traffic, detect quakes, and map fault structures. In the Pacific Northwest, researchers are experimenting with offshore fiber cables to detect both quakes and deformation signals that might relate to slow slip. Add to that the ocean-bottom geodesy networks, GPS acoustic systems that use buoys and seafloor sensors to measure tectonic motion offshore, and we're inching closer to a system that can track slow slip in real time. But detection is just step one. The real challenge is interpretation. Not every slow slip means a quake is coming. Many, perhaps most, are just part of the natural rhythm of the fault. So, how do we distinguish a benign sigh from a breath caught before a scream? That's where machine learning comes in. Seismologists are training neural networks to classify slow slip events, comparing them with past events, and looking for subtle changes in timing, speed, location, and associated tremor. By treating each slip as a data-rich event, they hope to identify precursors or warning signs embedded in the deformation history. One promising approach, pioneered by Bertrand Rueda-Leduc and colleagues at Los Alamos National Laboratory, involves analyzing acoustic emissions from laboratory fault experiments. In those tests, tiny shifts in sound precede stick-slip behavior, the lab analog of earthquakes. When applied to field data, the same algorithms have shown potential for identifying patterns that precede real-world slip events. Still, these models are new, and the Earth is a far more complicated laboratory than any benchtop device. In practice, this means early warning based on slow slip remains a probabilistic art. You can raise a flag when certain thresholds are crossed, like a slow slip event reaching into a previously quiet part of the fault, or tremor migrating in a new direction, but you can't yet say with certainty what will follow. But consider the alternatives. For much of seismic history, our warning time was zero. We learned of earthquakes only when the walls shook. With early warning, we gained seconds. With slow slip, we might gain days. Maybe more. It's a different kind of warning. Not a shout, but a murmur, a change in the rhythm, a breath drawn in. And as our instruments become more sensitive, our models more refined, and our networks more integrated, we may come to recognize those murmurs not as noise, but as meaning. A kind of grammar, soft but steady, written in the pressure of rock against rock, in the slow dance of fluids, and in the memory of faults stretching back through time. It's not prophecy, but but it is attention. And attention in the end is what keeps us safe. There's a kind of quiet relief in the stories that almost became disasters but didn't. Like a stove left on but never catching fire, or a near miss on a rainy road that leaves only a racing pulse behind. In geology too, there are places where the Earth nearly spoke in catastrophe, but instead chose to whisper. Regions where slow slip events occurred under watchful eyes, where scientists and satellites caught the ground shifting just in time, and the worst, at least for now, never came. These places are our lessons in attention. They don't just teach us about what happened, but what could have happened, and how close we came. Let's begin in New Zealand. The Cascadia Subduction Zone, running along the country's North Island east coast, is one of the world's most closely monitored tectonic boundaries. Here, the Pacific Plate subducts beneath the Australian Plate at a brisk geological pace of about 4 to 6 centimeters per year. That's fast in plate tectonics. And as it turns out, it's fertile ground for slow slip. In 2010, scientists with GNS Science observed a large slow slip event offshore from Gisborne. GPS stations crept eastward over several weeks, showing displacements of up to 3 centimeters, quiet but significant. At the same time, seafloor instruments recorded changes in pressure, and ocean bottom seismometers picked up bursts of deep tremor. No buildings fell, no lives were lost. But the implications were loud. The slip occurred near the shallow part of the fault, dangerously close to the trench where a megathrust quake could rupture. It was the first time researchers had caught such a shallow slow slip in the act, and it prompted a re-evaluation of tsunami models and regional hazard assessments. Since then, the Cascadia margin has offered a slow slip masterclass. In 2011, a similar event unfolded further south near Hawke's Bay. Again, GPS and tremor data documented the shift. And in 2019, a slow slip near the Kapiti coast continued for several weeks, marked not by damage but by subtle inland motion and a flutter of tremor beneath the Tararua Range. What's remarkable is how often these events repeat. Some fault segments along the Cascadia Trench slip every 1 to 2 years, like a metronome with just enough irregularity to make it interesting. Others go quiet for a decade. Understanding why some patches are rhythmic, while others are coy, is now one of the leading questions in the region's tectonic science. But here's where it gets even more compelling. In 2016, the Kaikoura earthquake, a magnitude 7.8 monster that tore through northeastern South Island, was preceded by a slow slip event offshore. In the weeks before the quake, GPS stations near the Cascadia margin had already begun to drift. Was it a coincidence? A trigger, a prelude? The jury is still out. Some studies suggest the slow slip may have increased stress on adjacent faults, others propose it was unrelated. But the timing was enough to shift the conversation. For the first time, seismologists began to consider the possibility that slow slip could be part of an earthquake cascade, one domino nudging another, quietly, across an invisible board. Half a world away, Japan has had similar brushes. The Nankai Trough is one of Earth's most seismically famous subduction zones. It has produced numerous devastating earthquakes over the past millennium, and it's due again. That dew hangs heavy, like an unsent letter. And yet since the early 2000s, portions of the Nankai Trough have been slowly slipping. Every few years, GPS stations in Shikoku and Tokai detect small motions, just a few millimeters, but coordinated across wide regions. Tremor follows. In 2006, one such event extended unusually close to the locked portion of the fault thought to be primed for a major quake. For several weeks, seismologists held their breath. But the quake never came. That event became a case study in both potential and restraint. It also led to expanded deployment of seafloor sensors and the development of Japan's real-time geodetic warning systems. Even in North America, we've had close calls. The 2003 slow slip in the Pacific Northwest, part of Cascadia's now famous 14-month cycle, brought new urgency to fault modeling. Not because it caused damage, but because of what it might imply. Researchers noticed that slow slip and tremor seemed to approach the locked zone beneath Vancouver Island more closely than usual. Again, no quake followed. But the event revealed the fault's capacity to change rhythm, to behave unpredictably even in a system that otherwise felt regular. And then there's Mexico. The Guerrero segment of the subduction zone south of Acapulco has become one of the most famous laboratories for slow slip. Since 1996, GPS data have shown that this fault undergoes large slow slips roughly every 4 years, each lasting several months, and releasing seismic energy equivalent to a magnitude 7 earthquake. In 2002, a Guerrero slow slip overlapped with a burst of low-frequency earthquakes and tremor, leading some researchers to suggest that the event came dangerously close to triggering a shallower quake. Once again, the earthquake didn't arrive, but the slip had spoken. So what do all these places have in common? They got lucky, or perhaps more accurately, their faults chose patience over rupture. But more importantly, they had the instrumentation in place to notice, to track, to learn. These moments become our tectonic what-ifs. They push us to ask better questions, refine models, and crucially, install more sensors. Today all of these regions boast dense GPS networks, seismic arrays, and increasingly ocean bottom observatories. These instruments don't prevent disaster, but they transform a silent slip into a recorded event, and a potential surprise into a teachable moment. And perhaps most crucially, these events help us understand how faults communicate. Because the Earth doesn't slip in isolation. A slow slip in one region may alter the stress in another. A tremor in one direction may pull on the tension in an adjacent segment. These interconnections form the skeleton of our emerging understanding of earthquake precursors. Not a crystal ball, but a web of causes and consequences. And every time the Earth decides not to shake, but to slide instead, we're given a fleeting chance to listen, to refine our vocabulary for tectonic behavior. The coastlines remain, for now, unbroken. The skyscrapers still stand. But below the surface the story continues to unfold. And we, if we're paying attention, might just learn to read between the lines.
Not all faults are born equal. Some are brash, impulsive, snapping to attention, with little warning and releasing energy in catastrophic bursts. Others are patient, deliberate, content to move quietly across the centuries. And in between are those that change personalities mid-sentence. Faults that sometimes slip in silence and other times scream. It turns out that the Earth has a surprisingly diverse social life beneath its crust. To understand why some faults favor slow slip, while others burst into classic quakes, we need to peel back a few layers of geology and physics. There's no single cause. Instead, it's a cocktail of depth, temperature, mineralogy, water content, stress, and history. A fault's biography written in stress-strain curves. Let's begin with the most basic difference, depth. Most slow slip events occur deep along subduction interfaces, typically between 25 and 50 kilometers below the surface. This zone lies beneath the brittle crust, where rocks are hot enough to deform ductily, that is to bend and flow rather than crack. Faults at these depths don't experience the same stick-slip frictional locking that causes classic earthquakes. Instead, they slip gradually, like warm wax under pressure. In contrast, the shallow crust, the upper 15 kilometers or so, is where earthquakes earn their destructive reputation. It's colder, more brittle, and less forgiving. When stress builds here, it tends to release in sudden, jerky fashion. This is the realm of sharp seismic shocks, high-frequency shaking, and broken ground. But it's not just temperature. Frictional properties of the fault matter deeply. Laboratory experiments have shown that different minerals respond to stress in dramatically different ways. Clay-rich fault gouges, for example, tend to weaken gradually with increasing slip rate, making them prone to stable sliding. In contrast, quartz-rich rocks often strengthen until they rupture, favoring seismic slip. In 1992, Jim Dietrich developed a theory called rate-and-state friction, which describes how a fault's friction changes over time and with slip rate. It turns out that some faults are inherently velocity weakening. They slip more easily when moving fast, and are thus prone to earthquake rupture. Others are velocity strengthening. They resist fast motion and favor slow, stable sliding. This framework has become a cornerstone of earthquake physics. It helps explain why certain patches of a fault slip quietly, while others store up stress and then fail catastrophically. Take Cascadia, for instance. Beneath the Pacific Northwest, the fault behaves differently at different depths. The shallow portion, locked and brittle, is the likely source of the future megathrust quake. Below that lies a transition zone, warmer, more ductile, laced with high-pressure fluids. This is where slow slip and tremor reside, performing their ghostly duet every 14 months or so. But even within this deeper realm, not all parts behave the same. Some slip consistently. Others seem to stutter, and a few remain inexplicably quiet. In 2013, researchers including Evelyn Roloffs and John Vidal analyzed data from Cascadia's episodic tremor and slip events and found that some regions consistently produce tremor, while others are repeatably silent. These quiet zones may represent locked areas of the deep fault, or places where slip occurs aseismically, without tremor. The same patchwork appears in Japan. Along the Nankai Trough, different segments of the subduction interface host different behaviors. The Tokai region, for instance, is locked and overdue for a major quake. Meanwhile, the Bungo Channel segment is a hotbed of slow slip, producing events every 6 years. And further east, the Kia Peninsula shows both tremor and occasional shallow slow slip, creating a layered mosaic of slip modes. Why the difference? Mineralogy plays a role. Sediments subducted at different locations carry different compositions, some rich in smectite clays, others in volcanic ash, carbonate, or siliceous ooze. These materials alter how faults behave under stress. Laboratory tests show that smectite, for example, promotes stable sliding, while elite and quartz promote seismic rupture. Add to that the role of fluids, which we explored earlier. High pore fluid pressures reduce the effective normal stress on a fault, making it easier to slip slowly. In regions where fluids are abundant, such as zones with active serpentinization or dehydration reactions, slow slip becomes more likely. But again, it's not so simple. Some faults with high fluid pressure still rupture catastrophically, and some with seismic mineralogy still slip quietly. So there must be something more, something dynamic. One candidate is fault geometry. Straight faults tend to behave more uniformly, but faults with bends, steps, or rough surfaces experience stress heterogeneously. Some patches become locked, others creep. The result is a complex mechanical interface that defies simple classification. This is particularly evident in New Zealand, where the Hikurangi Subduction Zone dips at a relatively shallow angle and receives a thick pile of sediment from the Hikurangi Plateau. These sediments alter the fault's shape and frictional behavior, creating a gradient from shallow slow slip in the north to locked zones further south. In Mexico, the Guerrero segment shows deep, long-duration slow slip events, while neighboring segments remain quiet or rupture seismically. Again, it's a combination of subducting plate features, sediment thickness, and fault lubrication that drives the difference. One fascinating wrinkle: some faults appear to change personality over time. In the 1980s, parts of the San Andreas Fault were thought to be mostly creeping, slipping steadily without earthquakes. But recent seismicity suggests that even creeping segments can host moderate quakes under the right conditions. Conversely, some traditionally locked segments have shown signs of aseismic slip. This raises the idea of fault evolution, that behavior is not fixed, but shaped by history. Every slip event alters the structure of a fault. Cracks widen or heal, fluids migrate, minerals transform. These changes feed back into how the fault will behave in the future. It's a geological memory, encoded in strain and fracture. As researchers like Yehuda Ben-Zion and Sylvain Barbet have shown in numerical models, faults can spontaneously evolve from steady creep to stick-slip behavior, or vice versa, depending on stress history and internal feedbacks. In other words, a slow-slipping fault today could become a seismic hazard tomorrow, or a once-locked fault could transition into a quiet slider. This has profound implications for hazard assessment. We can no longer label faults as safe just because they creep, nor can we assume that locked zones are always primed for the worst. Instead, we must consider the slip mode spectrum, a continuum of behaviors from steady creep, to slow slip, to low-frequency earthquakes, to classic quakes. Each mode exists in its own corner of parameter space, shaped by rock type, fluid pressure, stress, temperature, and geometry. And faults may move between these modes like actors changing costumes, depending on the role they're asked to play. Understanding this spectrum is the next frontier. It means combining lab experiments, field observations, satellite data, and numerical models into a unified framework. It means listening not just for earthquakes, but for tremor, for creep, for shifts in GPS, for changes in strain rate. And it means accepting that the Earth, like us, is more complex than categories allow. The next time you stand on solid ground, be it a sidewalk or a windswept ridge, know that beneath you may lie a fault with its own peculiar style. Some prefer silence, some speak in rumbles, some wait, listening, and some just maybe haven't made up their minds. There's something oddly comforting about slowness. A pot left to simmer, a long walk with no destination, the gradual unfurling of a fern.
In the world of tectonics, slowness can feel like a blessing, especially when it comes with no sirens, no tremors, no crumbling walls, but slowness, like silence, can carry weight and meaning. To listen to slow slip events is to be initiated into the patience of the planet. These aren't eruptions of motion, but ongoing processes, like a tide that arrives imperceptibly and stays. In watching them, we begin to learn how the Earth breathes, not in human minutes or days, but in geological months, years, and centuries. And as it turns out, that breath has much to teach us. Slow slip events offer a window into something rare in the earth sciences, a process that happens on observable timescales, yet mirrors the deeper, longer rhythms of the tectonic cycle. They are in many ways proxies for the invisible. They let us see how stress builds and releases. They let us model fault behavior, not in the static snapshots of past earthquakes, but in motion continuous, live, and brimming with subtlety. At first glance, it might seem like these events spread over days or weeks are too languid to be useful, but slow doesn't mean simple. Quite the opposite. Their very slowness gives us the luxury of time to observe, to measure, to model, to test hypotheses in ways that fast, violent earthquakes never permit. Dr. Laura Wallace, whose work in New Zealand has shaped much of our understanding of Hikurangi, slow slips, puts it this way. They're like natural experiments that run every couple of years. She's right. Imagine being a biologist who gets to study a rare species once a decade, then suddenly finds a dozen live specimens, each on a regular schedule. For geophysicists, that's what slow slips are. And so, we've begun to use them. In the Pacific Northwest, every 14 months or so, Cascadia's deep interface stirs, GPS stations twitch, tremor crackles in the crust, and models come to life. Scientists feed these real-time observations into simulations that refine estimates of fault stress, interface coupling, and seismic potential. They check for migration patterns, changes in tremor density, and subtle shifts in fluid pressure. In Japan, seafloor instruments along the Nankai Trough capture slow slips as they ripple beneath the ocean, providing data that feeds directly into hazard forecasts. These events aren't nuisances, they're field labs, and each one adds resolution to the portrait of a future megathrust quake, helping determine when, where, and how it might unfold. But even more than that, slow slips invite us to rethink time itself. Most natural disasters come suddenly, a flash flood, a wildfire driven by wind, an earthquake in the middle of the night. They interrupt. They rupture. They demand. Slow slips do none of that. They wait. They unwind. They unfold, at a pace that invites you to match it, and when you do, something remarkable happens. You begin to see the planet in process, not just in crisis. You see that tectonic plates are not fixed, but drifting. That faults are not dormant, but evolving, that the ground beneath you is less foundation and more negotiation, a constant bargaining between push and pull, stress and release. This perspective has begun to seep into other fields. In engineering, infrastructure planning is beginning to account not only for sudden quakes, but for long-term deformation, subtle warping of bridges, pipelines and railways caused by cumulative slow motion. In urban policy, emergency managers in regions like Chile and New Zealand are folding slow slip forecasts into readiness scenarios, using them to adjust alert levels or activate public education campaigns. Even in philosophy and literature, slow geological processes are being embraced as metaphors for resilience, for aging, for change too gradual to see. Because there's something profoundly human about slowness. It aligns with our need for stories, not just events. Slow slip events don't just happen, they arc. They have beginnings, middles and ends. They give us narrative structure, the kind you can follow and analyze, and in that narrative, we find a rhythm that's easy to miss, but impossible to forget once you hear it. The earth moves. Not just in shudders, but in sighs, and it remembers. Each slow slip modifies the fault ever so slightly. It wears away at the locked zone, alters stress distribution, encourages mineral transformation. It may even affect future slip behavior. Researchers like David Shelley have shown that tremor patterns change over time in response to past events, suggesting that faults are not just passive channels but responsive systems. It's the geological equivalent of muscle memory. A fault that has slipped slowly before may do so again. Or it may not, but it will carry the imprint of its past behavior. That history becomes part of its future. To study slow slips, then, is to engage in tectonic memory work, To trace the echoes of past motion in present patterns, this is why long-term monitoring is so important. A single slip tells us something. A decade of them tells us more. A century, if we're lucky, might finally let us predict. And so we watch, not just with satellites and GPS, but with new instruments, optical fiber, quantum gravimeters, borehole sensors. The deeper we look, the more layered the story becomes. We begin to see the interplay between crust and mantle, between fluid and rock, between brittle fracture and ductile flow. And we start to ask bigger questions. What governs the transition from slow slip to earthquake? How does the fault decide what kind of event to host? Are there signals, buried in the noise, that might let us forecast not just aftershocks but forethoughts? The answers are coming slowly, but that of course is fitting. Because slow science, like slow slip, is often the most profound. It teaches us patience and humility. It reminds us that understanding doesn't always arrive in thunderclaps. Sometimes it arrives in quiet repetition, in careful listening, in the willingness to stay with a problem long enough to let the planet speak. We live on a restless Earth, but not all restlessness is dangerous. Some is simply alive. And when we slow down enough to listen, we might just find that we belong to its tempo more than we knew. By now you and I have traveled quite a distance together, not just across tectonic plates or into subduction zones, but through time, deep and slow. We've listened to the Earth's murmurs, traced its invisible movements, followed whispers through fiber optic cables and tremors through granite hearts. All along we've been shadowing a question too large to answer, and too quiet to ignore. What do all these silent earthquakes mean? The final truth is both complex and calming. The Earth is speaking. It always has been. And now, at last we're learning how to listen. Slow slip events aren't anomalies or afterthoughts in the seismic catalogue, they are core to the Earth's mechanical life. They help redistribute stress, reveal the behavior of deep faults, and sometimes, just sometimes, they might even buy us time. Time to prepare, time to observe, time to understand. This understanding, of course, is still young. As young as the GPS constellations that first caught the slow shuffle of plates. As young as the satellite-borne radars that captured the Earth's twitch in millimeters. But it grows with each slip, each tremor, each wave of pressure caught in the tilt of a seafloor sensor. Let's reflect for a moment on what we now know. We've seen how slow slip events can span hundreds of kilometers, yet move no faster than fingernails grow. We've learned that GPS and INSAR, those patient eyes in the sky and on the ground, make it possible to detect these events with remarkable clarity. We've witnessed how the Cascadia Subduction Zone pulses like a clock, how the Hikarangi margin hums with slow, predictable release. We've followed tremor like a thread, low-frequency earthquakes that map out deep fault zones in the same breath as fluids escape from ancient rocks below. We've looked into fault fluids, how their subtle presence can lubricate motion or trigger chaos, and we've heard how these subsurface liquids influence the fate of a tectonic interface. We've explored the potential for tsunamis born not from abrupt violence, but from shallow slips, so slow they barely stir the sediment. We've watched scientists use slow slip events to build early warning frameworks, even if only for a moment's edge. And we've observed regions that got lucky, not because the Earth is kind, though it can be, but because we were paying attention when it sighed, instead of screamed. Faults, we now know, are as individual as people. Each has its own temperature, history, rhythm. Some shout, some creep, some switch languages mid-sentence. And all of them are more dynamic, more fluid, and more complex than our old maps allowed. But this is not a story of fear. It's a story of awareness. And of scale. To live on Earth is to live with movement. Not just the sudden kind that shakes walls, but the imperceptible kind that shapes continents. Mountains rise. Valleys stretch. Faults slip, pause and slip again. In a way, slow slip events are the Earth's self-regulation system, not always enough to prevent a major quake, but often the means by which tension breathes in and out, adjusting the load just slightly, shifting stress from one part of the crust to another. And in studying them, we see more than rocks. We see a planet in conversation with itself, grinding, sighing, murmuring across kilometers of depth and eons of time. The lesson isn't just geological, it's philosophical. Scientific curiosity reminds us that even the quietest forces deserve attention. That silence does not mean stillness. That calm does not mean peace. It means something is happening, slowly, steadily, with intention. And perhaps that's a reminder for us too, to move with thought, to listen longer, to accept the world's rhythms without always needing them to align with our own. Because in the long run, we are just passengers, riding atop plates that move not in bursts but in breath. So, thank you for joining me tonight, for walking with me across the hidden landscape of Earth's slowest earthquakes. If you enjoyed this little journey into the secret life of slow slip events, please consider leaving a like, subscribing, or leaving a comment. Sleep well, fellow traveler. The plates are whispering, and you're always welcome here.